Hi everyone, and welcome to episode 9 of Q for Problems. Today we'll be looking at problem 9 from the Project Euler problem set, and it wants us to find a Pythagorean triplet denoted by A, B, and C. So the question here shows the definition of that, of what a Pythagorean triplet is. And we want to find the one where A plus B plus C is equal to 1000 and then do the product of A, B, C. So let's have a look. Looking at the top formula group here, we have that A is less than B is less than C, and A plus B plus C equals 1000, which is what the problem gave us. From that we can deduce that A and B both must be less than 500. And from the bottom group, given in the problem was A squared plus B squared equals C squared, and then we've just rearranged the A plus B plus C equals 1000 formula, and that gives us the very bottom equation as shown. Using some algebra, so you can see how this was actually deduced looking at the GitHub page, which will be linked below. So hopping into our KX developer, we're going to use the equations that were shown in the previous slide to derive our solution 1. So our solution 1 is going to be building up all the possible combinations that A and B can take, and then finding the appropriate ones which satisfy the equation that was given. So firstly, we have that A and B cannot be greater than 500. So this means that we can just look at the numbers up until 499. So we first generate that list from 1 to 499, and then we want to get all the possible combinations, all the possible A and B combinations of this. So we just do n assigned to n cross with itself, and you can see that gives us all the cross combinations. So the next thing then is to look at the second formula, which I showed in the previous slide, and that was that 1000 minus all our A values. We'll say that's the first index of this list n. So here we leave the first index blank. That means to go over every row of this, and then the second index corresponds to the 0 index on each of these, which is the first item. And then we also want to do the product with 1000 minus and then all our B values, which is going to be the same thing, except we're going to take the 1 index, which is going to be the second item. So if I run that, you can see all these possible values, and remember now we want to check which of these is equal to 500,000. However, before I go on to that, I just want to make one small improvement. If we do 1000 minus here, i.e. rather than doing 1000 minus and 1000 minus on these separately, we can actually do it on both of them together and then do the product. So if I run this, you can see now we have all the possible combinations, but we've already done the 1000 minus each of them. And then all that's left to do is do prod each n. And you can see that gives us what we had before. So now we need to check where these values are equal to 500,000. So if I have my 500,000, and that will give me my Boolean list of true and false values where it's equal. We just want to find the indexes where that is. And you can see we get 2 indexes. So if I do n on that, you can see it's just the reverse of each other. We don't actually care. Even though it says A is less than B, it actually, for this problem, it does not matter in that case. So we can select either of these. So if I just do first on that, then we get the 806.25. However, the only thing is these aren't the actual values of A and B. These are 1000 minus those values. So because of the first part, we did 1000 minus this. So we need to essentially undo that part. So if we say A, B is equal to 1000 minus, and then this line here that we had up above, get that in and run that. So you can see now these are the actual proper A and B values. And the next thing then is to actually calculate C. So remember, C is just 1000 minus the sum of A and B. So if I just do 1000 minus sum, and then I just call this AB to say that this is A and B. And you can see that will give us our C value. And then the actual question wanted us to do the product of these. So A, B, which joined with this that gives us C value. So I do that, you can see now that this is the actual result. So our solution one then, I'm just going to copy it up. Looks something like this. And you'll see that everything we've discussed is actually in this. This is just it as a single line. And if I define this and run S1 with no arguments, you can see it gives me the answer. In solution one, we've seen that for each combination, we were actually getting the reverse form as well. So for the answer, we had 625 and then 800, but we also had 865. That's when we were trying to find A and B. So because we're then doing the cross and getting these repeated values, and it doesn't matter which order they are, we're actually doing extra work. So instead of doing the whole cross, we can just do essentially called a lower triangle. So it will be one plus till each, and then the n that we previously had, which was 1 plus till 499. So when I run this, you can see it's something that resembles a triangle, where in each iteration or each row, we're going up by 1. So it's going from 1 till 1 essentially, but we're doing 1 plus on it, so it's 1, and then 1 plus till 2, and then 1 plus till 3. So that creates this essentially half the values. And then to do the products, just the unique products rather than doing both forms of the reverse form as well. We can just do n times each both. So that will take our n, which is just our list of numbers, and multiply in turn. So the 1 will get multiplied by this, 2 will be multiplied by both of these, 3 multiplied by both of these. So if I run that, you can see we've got all those products. So that's essentially how we do the product. However, we need to do 1000 minus, if you remember from before. So if I instead put 1000 here, and then that's times each both of 1000 minus this, you can see now that this is similar to the combinations we had before. However, this time it's a list of lists, which makes indexing it slightly more complicated. So that's what we need to deal with next. So if I assign this to P for products, so now we need to check where P is equal to 500,000. So if I do P, 500,000 equals P, we see we get this Boolean triangle where there'll be a true value wherever there's 500,000 match, and we only have one of these in this whole triangle. We can't actually see it here because the triangle is so large, but we will be able to find it. So if I do where on each of these rows, you can see what it gives me here is nothing. Essentially what it's doing is saying, trying to find the index for each row where there's a true value for those rows, which is all but one row where there's just all falses. It's going to be an empty list because there are no indexes, which is why it's showing up as nothing here. But there will be one row with one value. So if we want to find the index of that, so I'm going to just assign this to W. We need to find the row and the column. So we'll do the row first, and we'll assign this to A. So what this is going to be is it's going to first be the count of each W. So I'm just going to run this small part first. So you can see they're all 0, all but one of them will be 0, because there was 500,000 is only going to be found in one place. And we want to find where there's actually a count greater than 0 essentially. And you can see there it's returned 1 index. So that's the actual row that it's found in the triangle. So it's on the index as shown. And as you can see, it's given us as a list form, but we know it's going to be always one value. So we're just going to do first not just to flatten it to a single item. We also need to do the column. That can just be done as first W indexing the I. So I was the row, remember? So if I actually look at that row then, and you can see here that it's only got one index in it. So remember that W is the indexes where it's found on each row. So if we want the column, then we can just first go to that row, and then you can see that this is going to be the column index already given. So we just do the first again to flatten that to a single item. And from there, it's similar to what we had before. So we just do A, B, which is the A and B joined together, and that's going to be our original list. It's going to be indexed by both of these items. And so if I run that, you can see that gives us what we had before, 375 and 200. And then it's going to be exactly the same then as before, just to do the 1000 minus the sum AB to get C, and then do the product over all three of those values. And you can see that's what we had before. So the actual S2 solution here is, I'm just going to paste it in just as one function. Would look something like this. So when I run that S2 with no arguments, you can see that gives us the answer. For solution 3, we'll use a property of Pythagorean triplets. That is shown by the top three equations. So A is equal to 2mn, B is equal to m squared minus n squared, and C is equal to m squared plus n squared. So here m and n are integers where m is greater than n and they're both greater than 0. And shown in the git notes is the derivation of how we arrive at the bottom two results. So it can be shown that n is equal to s over 2m all minus m, and then that the value of m must lie between the square root of s divided by 2 and the square root of s over 2. So have a look at the notes if you want to see how these two formulae were derived, but we'll use these now to create solution 3. So hopping over to our developer, we are going to look at the case where s is 1000 in our particular example, as the question gave us. So setting s equal to 1000. Now we're going to find the possible range of values that n can take. So in the upper and lower bound, we had the square root of s on the numerator of both the fractions. So doing square root of s, now that the denominator should be divided by. In the lower bound case was just the number 2, and the upper bound case was actually the square root of 2, so we're going to just join those together. 2, so you can see that this is going to be a list of two values, this 2 and the square root of 2, and then we're going to do the square root of s divided by both of those values, which you can see gives us these decimal values. So from here, it would be simple enough because we have a m is greater than, strictly greater than, not equal to the lower bound, and less than and not less than or equal to the upper bound. We should round the lower bound up to the nearest integer and the upper bound down to the nearest integer because m is an integer value. However, that doesn't always suffice, because if I say set s equals to 200 and do it for here, you can actually see here that the upper bound is already an integer value. It's already 10. However, in this case, remember, m can't be equal to the upper bound, which means we'd have to go to the next one down, which means this should actually be 9. So we can't just simply round these values up and down respectively. We actually can instead use 1 and minus 1 plus. So that does, this number will be plus 1, and this the second number will be minus 1, as you can see. And then we can do our floor on the lower bound and ceiling on the upper bound to round them to the nearest integers. And we can apply both to apply the floor to the first number and the ceiling to the second. So when I run that, you can see now that gives 8 and 9. So that's why we have to do it like this. So I run that again, 1000. There we get our range now of possible m values has to lie between 16 and 22 inclusive. So we'll say that's R for our range. Now we can calculate our possible m values using a function that was previously described in episode 4. So go check that out if you want to know how this works. But it will essentially just create a range between 16 and 22 inclusive. So if I run that, you can see we have a range of integers between 16 and 22. So these are the possible values of m. So what we need to do now is derive the n, a, b, and c values from these possible values. And then from there, we can test to see which ones are actually correct. So if I calculate n first, so these are going to be using the formula that were shown on the previous slide of the equations. So you can compare them there to see that they do, in fact, agree. So that's, as you can see as well, we're calculating this as a vector, so we're doing all the possible values in one calculation. So A was simply just 2 times m times n, so we can run that. B, so for B, we wanted to do the m, n, we're both to the 2 n to the power of 2, so it's x exp function 2, so that takes all these values to the power of 2. So I run that, you can see we still have the two lists, the top one being the m values to the power of 2 and the bottom being n values to the power of 2. However, just one note is that the x exp function actually returns a floating point value. So even though these values are whole numbers, the actual underlying data type has been changed. So I will cast here to a long, just to make sure they're still of type long. And we can, because we're going to use the square of m and n in the calculation for C, we can save this value too here, just so we can reuse it without having to redo this part. And then what we want to actually do is to minus, so take the second list from the top list. So we can do that just doing a minus dot apply. And then if we run this, we can define B. And C, we could do a plus apply for C, but we can also just use the sum function, m and 2. So that can save us one character. So that's our A, B, C, and N, and we have M as well. So now that all we need to do is test which A, B, and C values actually agree with A plus B plus C is equal to 1000. So if I wrap these three values in a list and just run this so you can see, so the top row is A, second row is B, and third row is C. And it is the possibility, although not the case here, that these values can be negative, in which case we just want to do a zero minimum or maximum with that. So if there are negative values, it just puts them zero because we know a negative value isn't right. So if we zero it out, that means then that that column can never equal our 1000. We also then want to do, we'll assign this to V to keep it for later, and we want to do the sum. So if I run that, you can see here's all the sums, and you can see there's one here that agrees and says it's equal to 1000. So we would want to find those values. So we do s equals to get the boolean, and then we do where to get the index. So you can see here that the index is a list. In this case of 1000, there only is one Pythagorean triplet. However, for some numbers, there can be more than one triplet, which is why we have to keep this as a list. We can't just take the first at this point, for our general function at least. So we can index back into that V that we saved then to get the A, B, and C values. So remember, V is a list of lists. So we leave the first index blank, which means to go to each row, and then from each row take the ith element. So you can see here that these are the three values that we did have in the previous solutions. In the case of our the chance that we actually have two or more values, we would actually need to do a flip to get multiple rows. So each row then is a corresponding Pythagorean triplet. So that'll make more sense in a minute whenever I introduce another function. However, we can put this all into our function. I'm just going to paste it in here, and you'll see that this is exactly what we had before. So that's pi triplet. So if I run pi triplet on 1000, you can see there that's our three numbers. If I do it on 720, here you can see there's actually two possible Pythagorean triplets. And if I do it, say, on the number 10, there are no Pythagorean triplets, so it just gives us an empty list. So it still works in the case where there are no values. And then this is just an aside function. This won't be using the solution 3, but we can generate here all the Pythagorean triplets up until a certain given number. So if I put in that and say all the Pythagorean triplets up to 1000, you can see what it gives me is the key is the actual value. So 12 is the a plus b plus c, and then these are the three Pythagorean triplets, and you can see some of them do have multiple ones. Just note that these aren't just the primitive Pythagorean triplets, which means, as you can see here, 12 and 24, that 24 list is just double of 12 one. And you'll see then you can see 48, you can see 96. So the primitives would be just the base elements essentially. So the one that can be factored down to the lowest. However, this function just gives us everything. But that's just an aside. So the actual then solution free, we can define as solution free because remember we want the product of A, B, and C, so we do prod, and then we need the first because for the one in question here that we're doing, the 1000, um, it's only ever going to give us the one list of the numbers because we know there's only one, so we can just do first on this because remember this gives us a list of lists, so the first will just take the first list, which is going to be our Pythagorean triplet. So defining that, and then S3 on 1000, and then run that, and as you can see, that gives us our answer. So looking at performance, we have our S1, S2, and S3, and we will run our performance test here. And we can see here for N is 100, so we run each of them 100 times just to get a good average. We can see here the memory usage and the average time taken for S1 compared to S2 and S3, and you can see that S3 is by far the best. It is an order of 100 better than even S2 in terms of time, and the memory is just a lot better. So just using this numeric approach is a lot better than the brute force approach we took in S1 and S2. So yeah, that's everything. Thanks for watching. Please share your solutions. Check out the Git if you want to see the derivation of any of the formula. And yeah, I'll see you in the next episode.